If you guys could go to the slide that says, what about when you don't have points? I want to explore a stranger situation, right? Like a situation where instead of having these discrete points that we can just put into our little formula, right? X, center of mass, is equal to the sum of the position, the x position of each guy times the mass of each guy, divided by the sum of all the masses of each point, okay? But here, we don't have individual points, okay? We have this situation, we want to find the mass of like this chunk of metal where half of it is iron and half of it is aluminum, all right? And we don't have a nice little point. Now, here's the thing. If this were, all iron or all aluminum, if this were homogeneous, it would be totally symmetrical. And symmetrical objects that don't have any change in density from one end to the other, those guys will always have a center of mass right in the middle, right? Just imagine a yardstick. A yardstick is basically this, like a rectangular prism, right? It has 3 dimensions, a length, width, and a depth, right? And it has a certain length, and that if I were to find the center of mass of that, it would be directly in the middle. Like a meter stick, it would be right at the 50 centimeter point, right? So it would totally balance there. But why is this harder? What makes this problem harder? It's the fact that it's not symmetric. We have half of it being iron and half of it being aluminum. And as the problem states, the density of iron is much higher than the density of aluminum. To be specific, the density of iron is equal to 7.85 grams per centimeter cubed. Okay? And the density of aluminum is going to be much lower, 2.7 grams per centimeter cubed. Okay? Now, what does this tell us? That tells us that, so if this is the y-axis, it tells us that we would expect, since more mass is concentrated in the iron, we would expect that the center of mass would be a little bit skewed towards the iron along y, right? But notice that in Z, right, there's no change in density, right? The object is not changing at all, right? So that should be totally symmetric. And in X, right, along here, there's no change in density in this direction. So that should be totally symmetric and right in the middle, okay? But that's not the case for Y. Y, it's going to be skewed one way or the other, and since there's more mass in the iron, it's going to be skewed towards iron. So let's start with the easiest part of this, right? Let's start with, so we know that that every center of mass coordinate is going to be an X, a Y, and some Z to find exactly where that point is, okay? And so that's going to be some X, some Y, and some Z, right? Let's start with Z. Z is going to be easy, right? Because, again, this is totally symmetric. There's no change in density as you go along the Z-axis. So that means the center of mass should be right in the middle, right? And so that means basically half of D2, whatever D2 is, and this problem says D2 is 2.8. Half of D2 would be 1.4. That should be the center of mass for Z, 1.4 centimeters. Okay, and because we're just finding a coordinate, we don't have to worry about SI units. We can have it be in centimeters if we want, as long as we make sure our density is also in centimeters. So now, same thing with X, right? If this is the X direction right here, there's no change in density here, right? It's the same amount of iron and aluminum the whole way down, right? So again, for X, that should be right in the middle, so it should be exactly half of D3. It says that D3 is 13. Half of 13 is 6.5 last time I checked. Actually, this is going to be for X, so 6.5 centimeters. Okay, so X and Z are totally easy because it's just halfway through, right? Now the problem is that as we go along Y, things change, right? We go from iron and now to aluminum. So in the Y direction, the center of mass should be skewed one direction or the other. How do we deal with that? Well, we treat iron and aluminum as two separate objects with the center of mass being at the middle of those two objects. Okay, so let's see how that plays out. I'm just going to switch this to Y here. We're trying to find the Y center of mass. And I'm going to make this going to be YI. Okay? So the y center of mass coordinate is going to be I equals 1 is going to be iron, I equals 2 will be aluminum. Okay? So the y center of mass of the iron is going to be halfway, like the middle of the iron block, which is halfway through D. Okay? D1. And D1, it says is 11, right? So halfway through that should be 5.5. Correct? So the center of mass is going to be the middle of iron, right, which is half of D1, which is, D1 is 11 centimeters, so half of that is 5.5, okay? Times the mass of the iron. Now, we don't have the mass of the iron, and that is complicated, okay? So what do? We employ a little trick, okay? And remember, and maybe I'll use this guy here. So remember that mass is equal to density times volume, right? So, but in this case, the volume of iron is the length times width times height. So the mass of the iron should be the density of the iron times D1, D2, D3, right? So you're going to see how this is going to play out in a second, but I'm going to roll with this right now. So I'm going to say that the mass, my Mi, right, is going to be the density of iron, which is 7.85, okay, times D1, D2, D3. And I'm not going to put those values in, and you'll see why in a second. D1, D2, D3. Okay? That's my first term. That's the term for iron. Okay? Now let's do the same thing. Plus, what is now the center of mass of aluminum? Well, it's D1 plus another half of D1, and I believe that should be 16.5. Should it be? Should it be? What is it? Yes. OK, it should be. So D1 is 11 centimeters, right? Plus half of D1, which is 5.5, ends up being 16.5. So 16.5 times, now we find the mass of the aluminum, so we just put A's here, right? So the mass of the aluminum should be the density of aluminum, which is 2.7, okay, times, again, D1, D2, and D3, the volume, okay? And this is all going to be divided by the mass of everything, which is going to be 7.85 D1, D2, D3, plus, right, that's the mass of iron, plus, I'm going to erase this now, the density of aluminum, so that's 2.7 D1, D2, D3. Now, this is why I kept these D1, D2, D3s as they are without canceling them. They all cancel, right? I can pull D1, D2, D3 out of both of these terms, and I can pull D1, D2, D3 out of all these terms. You have the same thing in every term. They're going to cancel out. Okay? That makes life much easier. So that really just reduces our problem to 5.5 times 7.85 plus 16.5 times 2.7, right? All divided by 7.85 plus 2.7, okay? And so if I just go ahead and multiply that, add it to those guys multiplied, divide it by these two guys added together, I get a value of 8.3 centimeters. Okay? Now, remember, D1, again, is 11, right? So is 8.3 less than 11? Is it closer to the iron side as we expect? Hell yeah, it is, right? So this is a pretty good indicator that we're in the right ballpark. We don't know for sure, but you guys could do the same math and prove it to me. But we do know that we're getting in the iron section of it, which is what we should expect, okay? And I can put 8.3 there. So just to recap, that was shameless, sorry. Okay, so just to recap, we were able to take this weird kind of mixture of iron and aluminum and find the center of mass by using arguments about symmetry. We know that nothing changed in z, right? The density doesn't change in the z direction, so that should just be 1.4, right? The density doesn't change in the x direction, so that should be 6.5, or half of d3, okay? But the density does change along y, and that makes things more complicated, but we can still use this formula if we consider each of these points to be the middle of the iron and the middle of aluminum, and find the center of mass between those two things. All right? And then we did this cool little trick where instead of masses, we said that it's density times volume. We let the volumes cancel out. We get a nice simple thing that we can just put in our calculator, find an answer, 8.3. We have now the center of mass of this weird object. Okay? All right. There are many, many places to practice these. This is just the bare bones. I am not going to make you do center of mass problems that involve integrals. There are many center of mass problems that involve integrals. I think that's unnecessary at this level. But I do want you to find other examples like this where you get comfortable finding the center of mass of objects where you have to find the middle of them, right? And use maybe the fact that there's different densities in different materials to find the overall center of mass, okay? There will be resources both in your book as other problems and in the online textbook on the syllabus and Khan Academy as well if you want to find other problems where you're finding center of mass. Okay, reach out to me if you have any questions, and I think that should close the center of mass portion of this lecture.